Hello everyone. In this video, we will discuss about the heat transfer mechanisms, and Fourier's law, which is comes in the conduction of heat transfer or conduction in detail. We know that the heat transfer means simply the transfer of heat, and it is defined as it is a process in which the transfer of heat from higher temperature system to lower temperature system. This is the heat transfer, and this is done by three mechanisms: first conduction, second convection, and third radiation. So conduction means what? Again, the transfer of heat from one atom to another atom or one molecule to another molecule within the same material, within the same object. This is known as the conduction. But in conduction, the flow of heat will depend on the transfer of vibrational energy from one molecule to another molecule, and in case of metal, the movement of free electron. This is a conduction. In case of the convection means the transfer of heat or heat flows is achieved by the actual mixing of warmer portion with the cooler portion within the same medium, and the convection is due to the bulk movement of this medium. This is a bulk phenomena. Okay, and radiation means the transfer of heat or flow of heat in a space in the form of electromagnetic waves, or we can say the heating source emits the radiation in the form of electromagnetic waves. Okay, this is called as the radiations. Now we see the conduction part in detail. The thermal conduction is the transfer of heat by microscopic collision of particle and movement of electron within the body. Okay, as definition says here. In this part, the basic law of heat transfer by conduction can be written in the form of rate expression or rate equation. And what is that rate equation? Rate is equal to driving force upon the resistance. This is equation number 1. See, in this equation, the driving force is the temperature drop, or we can say the temperature difference, or it is also called that is a temperature gradient, and the resistance. So driving force and rate, it is a directly proportional. So therefore, the greater will be the driving force, the greater will be the rate of heat flow, right? The flow of heat will also depend on the conductivity of the material through which it is flowing. For the transfer of heat, the conductivity of the material is very important. For example, here the conduction of heat is faster through iron rod than wooden log. Why there is a difference? Because wooden log has not that much capacity to carry the heat. Why? Because it creates some resistance for the transferring of the heat, and this resistance is denoted or expressed by, determined by the Fourier's law. And what is that Fourier's law? Or by this Fourier's law, the resistance term is expressed. What is that actual resistance? According to Fourier's, the resistance is equal to thickness of the surface divided by the proportionality constant into area of surface. That means L divided by Km into A. And this equation for resistance which obtained from this Fourier's law. But what is the Fourier's law? What is their statement? Here, here is the statement of this Fourier's law. Fourier's law states that the rate of heat flow through uniform material is proportional to the area and temperature drop, and inversely proportional to the length of the path of the flow. See, here the rate of heat flow through uniform material is proportional to means that directly proportional to area and temperature drop, and inversely proportional to the length of path of flow. Length of path of flow means the thickness. So equation becomes the rate of heat flow directly proportional area A into temperature difference delta T divided by thickness, which is in L. Rate of heat flow is denoted by the Q, small q, is directly proportional to A delta T upon L. If you want to remove this proportionality sign, we put here the proportionality constant Km. Now equation becomes the Q is equal to Km into A delta T upon L, and this is equation number 3. If we derive this expression, if we derive this law, we consider here the metal rod or metal wall for the flowing of the heat. Here the diagram of this for the derivation of the heat Fourier's law. This is a metal rod. It has the two walls or two faces, H and H, and here the C and C, and flowing of the heat from right side to left side. So therefore this is a direction of heat flow from right to left. Here the T1 and here it is a T2. T1 has the greater temperature, means here the higher temperature side, and T2 is a lower temperature side, and thickness of this metal wall is a capital L. Now their explanation is the area of wall A, thickness of wall L, face of wall HH is maintained at uniform, definite and higher temperature is equal to means T1. Face of wall CC is maintained at lower is equal to T2. The heat flow will be the right angle to the plane A and is assumed to be in steady state. Means flowing of heat is in right angle to that particular metal wall A. So therefore it is a steady state of heat flow. Consider the thin section of thickness dl at an intermediate point in the wall. In this diagram, this is the intermediate point dl, intermediate point of this metal wall dl. You can say the thin section dl, and on this thin section the Fourier's law may apply here. So now equation becomes the dq by d theta is equal to minus ka into dt upon dl. dq by d theta, this is the rate of heat transfer. Q means heat transfer, minus ka into dt by dl. Why dt by dl? Because this is a this shows the temperature drop or temperature difference, dt by dl. So Q is heat transfer, theta means time, K proportionality constant which has the unit, the watt per meter Kelvin, T temperature, and minus sign is there. Minus sign indicates the decrease in temperature. Means T1, suppose the T1 is a 40-degree temperature, and this flow of heat transfer through the metal wall, and the flow of heat or heat is reaches towards the T2, the temperature will goes on decreases, means T2 is the less as compared to T1, means we can say that T2 is a 20 degrees Celsius, right? Means T1 is 40 degrees Celsius and T2 is a 20 degrees Celsius. Means here the decrease in temperature, and this decrease in temperature can be shown here by sign minus sign. Okay. Now for steady state of heat transfer, this equation changes to, if there is a steady state of heat transfer, means flowing of heat is a perpendicular to this metal wall. Now dq by d theta means rate of heat transfer is a constant. So therefore we can put the small q instead of this dq by d theta. Q is equal to minus ka into dt by dl. So therefore this is equation number 5th. Again in the next step, rearranging this equation number 5th, q is equal to minus km into a into delta t upon l. What is the difference between these two equations? Here in the equation number 5th, instead of this dt by dl, we put here the delta t upon l. Delta t means here again the temperature difference, right? L is the thickness of this metal wall, capital L. In steady state of heat transfer, this q is remain constant, and so therefore the rearranging equation 3 by comparing it with the rate equation. What is the rate equation? the rate is equal to driving force upon resistance, right? And your equation number 6 and equation number 3 is the same. So therefore these equation is compared with the rate equation. In the rate equation, driving force is what? The temperature drop or temperature difference. And in this equation, the temperature drop is the delta T. Okay. So therefore the Q is equal to delta T divided by, if driving force is a delta T, then remaining part means Km and A is shifted to denominators. Means L divided by Km into A. This is equation number 7. And this equation compared with the rate expression, this term delta T indicate the driving force, and whatever the denominator part, this indicate the resistance, and this resistance is L divided by Km into A. Here we can see here the Q is equal to delta T. Delta T means the driving force, and denominator part is L divided by Km into A is a resistance. By this equation we can determine the resistance in quantitative manner. So therefore the Fourier's law is used to define the resistance in quantitative term. This is a Fourier's law statement or Fourier's law derivations for obtaining the resistance in quantitative manner. Thank you for watching.